Welcome back to another explainer. I'm absolutely thrilled you're joining us today because we're tackling a concept that literally transforms how we understand math. We're going to build your visual intuition for calculus completely from scratch. So let's just dive right in. We're talking about graphs. They're basically this magical tool that takes dry, abstract equations and turns them into beautiful, clear pictures of change. If you've ever felt, a bit intimidated by functions or derivatives, don't worry. This is the explainer that's going to make it all click. Here's our roadmap for today. We'll kick things off with mapping the math world. Then we'll move on to finding your coordinates, from equation to picture, the visual meaning of calculus, and we'll wrap it all up with the robot on the road. Section 1. Mapping the math world. Okay, think of a classic treasure map. If the hidden treasure is exactly 3 steps to the right and 2 steps up, you can find it without breaking a sweat, right? Well, in math, we just write that as a set of numbers in parentheses, like 3, 2. Coordinates are really just simple instructions for finding a point. To navigate this kind of map, we use 2 roads, basically 2 lines crossing each other. The horizontal line is the x-axis, and that controls our left and right movement. The vertical line is the y-axis, which handles moving up and down. Now, you might stumble across some old-school math words in textbooks. The x-coordinate is sometimes called the abscissa, and the y-coordinate is the ordinate. But hey, do not let these dusty old math terms scare you off. Abscissa just means x, and ordinate just means y. That is literally it. And right exactly where those 2 roads cross, we have the origin. This is home base. Its coordinates are simply 0, 0. And honestly, it makes perfect sense why. At this crossing point, we haven't moved left, right, up, or down at all. We're sitting at 0 horizontal movement and 0 vertical movement. Every single journey on a graph starts right here. Section 2. Finding your coordinates. So because our 2 axes cross right in the middle, they naturally chop our map up into 4 distinct regions. We call these quadrants. And this setup brilliantly shows how positive and negative numbers tell us exactly where we're standing. Up in quadrant I, the top right, both your x and y are positive. You moved right and you moved up. In quadrant 2, you moved left and up, meaning x is negative, but y is positive. Down in the bottom left, quadrant 3, well, that's the negative zone. You went left and down, so both x and y are negative. And finally, over in quadrant 4, you're moving right but down, making x positive and y negative. Once you've got these simple positive and negative rules down, you can instantly pinpoint exactly where any coordinate pair belongs on the map. Section 3. From equation to picture. Okay, this is where things get incredibly exciting. We are moving way beyond just plotting single points on a map. Now, we're going to translate entire mathematical equations into full-blown visual pictures. Let's take a look at the function y equals x squared. This equation is just a rule saying our y value depends on whatever our x value is multiplied by itself. So if we choose an x of -3, -3 squared gives us a y of +9. If x is -2, y is 4. If x is 0, y is 0. And if x is 3, y shoots back up to 9. By simply changing that input x, the function magically spits out a new y, giving us a whole sequence of coordinate pairs. And if you were to plot these specific points on our map and connect them all smoothly, you wouldn't just have random dots, you'd see a beautiful, perfect U-shaped curve. Now, sometimes mathematicians like to use the word locus to describe this. I know, it sounds like some intimidating, complex term, but it actually gracefully defines a super simple idea. A locus is literally just the complete collection of all the points that follow a particular mathematical rule. So every single point on that U-shaped curve, it belongs to the locus of points that satisfy the rule y equals x squared. A quick but really important side note here. A graph doesn't even have to be one single connected, continuous piece. Some math rules actually create jumps or separate floating sections. But even if there are gaps in the curve, all of those generated points are still part of the exact same picture. They're all part of the graph for that single function. So let's distill graphing down to a concrete, easy-to-follow checklist. Step 1, choose an x value. Step 2, calculate the y value using your function's rule. Step 3, create your coordinate pair, x, y. Step 4, plot that point on your map. Step 5, repeat this many, many times. And finally, step 6, watch how that collection of points smoothly forms the graph. You put numbers in, you get pairs out, you plot them, and boom, you've got yourself a curve. But let's pause for a second. Why are we doing all this? Why is this visual picture so absolutely crucial for understanding calculus? I want you to really chew on this for a moment, because this right here, this is the most critical conceptual leap of the entire explainer. Section 4, Visual Meaning of Calculus. This is where the magic happens. We take these static, unmoving pictures and turn them into dynamic, living stories of change. In calculus, you hear a lot about derivatives, which is often written as dy over dx. Basically, a derivative just tells us how quickly y changes as x changes. But I want you to look at this visually. When a graph is physically climbing upward, as x gets bigger, y gets bigger, that represents a positive derivative. The steepness is greater than 0. On the flip side, if the graph is sliding downward, y is shrinking as x grows. That perfectly illustrates a negative derivative. The physical direction of the curve is exactly mirroring what the abstract derivative is calculating behind the scenes. So what happens when the derivative is exactly 0? Well, think back to our u shape for y equals x squared. Right at the very bottom of that u, the curve stops going down, but it hasn't quite started going up yet. For one split second, the curve becomes completely perfectly flat. At that exact flat bottom, your derivative, your slope, is 0. The whole crucial point here is summed up beautifully in this quote. The derivative is the mathematical description of how the graph is changing. Imagine zooming way in on a tiny microscopic piece of a curving graph. If you zoom in enough, that tiny piece just looks like a straight line, right? The derivative is just telling us the instantaneous slope, the exact steepness of that tiny, zoomed-in piece of the curve. Pulling this all together, let's look back at y equals x squared. Notice how the equation, the visual shape, and the changing slope are all connecting at the exact same time. At x equals -2, the derivative, which happens to be 2 times x, is -4. The graph is decreasing. It's going downhill. At x equals 0, the derivative is 0. The graph is totally flat. And at x equals +2, the derivative is +4. The graph is increasing. It's heading uphill. One simple equation is telling us a completely cohesive story of change. Section 5, the robot on the round. To really cement this in your mind, we're going to use a brilliant analogy from our source material, a little robot going for a walk. This perfectly separates the mathematical rule from the visual picture. Think of the function itself as the set of rules. It tells the robot exactly where it's allowed to go. The graph, on the other hand, is the physical road itself, drawn out on the ground for the robot to walk on. And here is the final piece of the puzzle. As the robot walks along this physical road, the derivative is an instrument telling the robot exactly how steep the road is at that very microsecond. Is it a tough uphill struggle, a nice flat rest area, or a fast downhill slide? Calculus is simply the tool we use to measure the steepness of the road our robot is walking on. So let's look at the complete chain we've built today. We started with a function, which is just a simple rule mapping inputs to outputs. We turned that into a graph, our visual road. Then we looked at the slope of that road at any given point, which gave physical meaning to the derivative. And that derivative is fundamentally our instantaneous rate of change. See how every single concept just flows seamlessly and directly into the next? So, I'll leave you with this question. Will you ever look at a dry textbook equation the same way again? Or will you now and forever see a hidden, dynamic picture of change just waiting to be drawn? Keep exploring, keep graphing, and remember that every mathematical rule is just a beautiful picture waiting to be uncovered. Thanks for joining me on this explainer, and I'll see you next time.